I'm going to go into marine biologist, so I am a marine biologist. I did my PhD in Liverpool University, and I studied how seaweeds grow on shores, and different populations grow in different places. I then moved to Germany to look at seaweeds, or continue looking at seaweeds, but when I was there I started playing around with different kinds of marine organisms, and that brought me eventually to work in the Antarctic, in the Southern Ocean, which is what I'm going to talk about largely today, but subsequently I've gone on to work in the Arctic and also in the frozen Baltic Sea as well. So I spend a lot of my time working in ice in the Baltic Sea over the years. I've been in Bangor for 22 years, although many of my colleagues would actually not disagree with that, because of my job, I've been traveling quite a lot of the time, so they would probably say I've only been there for half of that time. Yeah, they're just jealous, really. So we're going to look at life on and within pack ice, and it's going to be a mixture of several different parts of the world as we get there. But it was all done. So modern science is a great thing, but it was all done in 1606, or actually in 1590, when this map of Iceland was drawn. And you'll see in the top right-hand corner, you'll see a very good depiction, well, just about, believe me, all this white fuzzly stuff is ice floes with a couple of polar bears sitting on it. So it's a bit of an ancient science. And I'm going to read this to you because it does make sense. Huge and marvelous, great heaps of ice brought hither with the tide from the frozen sea. So already we get a concept that it's actually a big, important thing. Huge, marvelous heaps of ice. You know, it's not a small, localized kind of system. And that the tides are important. The tides are kind of moving this stuff around. So the ocean currents are moving this stuff around, making a great and terrible noise. Anybody who goes on a ship into the frozen pack ice will know this. It is especially a metal ship. The scrunching and the scraping of the metal hull against these ice slabs is a terrible noise. In fact, it's a terrifying noise the first time you hear it. It is. So some pieces which oft times are 40 cubits big. 40 cubits is huge, so it's probably all of the buildings in this street and a couple of blocks wide. I mean, it's a massive thing. So they're obviously talking about icebergs in this case. So we're talking about icebergs being important. And upon these, some places, white bears do sit closely. Well, the white bears are clearly the polar bears. Watching the silly fish. Silly in these terms, in this language, does not mean stupid. It actually means curious. Watching the curious fish which here do play and sport themselves. So you've got this concept of a massive physical presence of the ice, which is daunting and intimidating and hostile. You've got the whole concept of ocean currents playing it, so it's all being moved around by the oceanography of the system. And you've got the ecology there. You've got white bears that are actually, they're not just watching the fish, they're probably catching the fish to eat. So effectively, and hopefully, I'm not going to come back to this slide, but you'll see that the whole of my lecture was worked out in 1606 when Hexham translated this text. Menai Bridge. Well, why do you do ice research in Menai Bridge? Well, it's a bit of a curious thing, isn't it? Well, we have had frozen ice on the Menai Strait in 1963. I've never seen any other record of frozen ice on there, but in 1963, the Menai Strait did freeze over, and actually would have been a fascinating place for me to have been. But we have I've been there, as I said, for 22 years, and in those 22 years, we've had constantly a group of people that have been working on Antarctic, Arctic, and other frozen realms as well. And we have a big group that are working in the Arctic Ocean, physical oceanographers at the moment, that are spending quite a lot of their time studying the changing Arctic Ocean as we are. So although you say, well, surely it's the British Antarctic Survey that does all of the polar research in Britain, there is a strong group here in Menai Bridge with a good history as well, despite us not having it. So this is what I'm going to talk about, and I'm going to show a little video now if it works. You will all be aware of this typical shape of the Antarctic, with a bit sticking up in the top left-hand corner there, and a big bulbous bit round in the East Antarctic. All of this stuff, the map, is continental ice. So it's mountain ranges and land that is covered in a sheet or sheets of frozen snow, effectively. some of those sheets several kilometres thick, so they're massive lumps of ice. So that's what we know as the Antarctic continent. What I'm going to ask you to look at is this girdle of white stuff. It's a pity it wasn't coloured somehow differently. This girdle of white stuff that you're going to see, and that's the pack ice. That's frozen seawater, and that's what we're interested in today. We're going to start in August. So it's in August down there. It's kind of winter down there. So it's the height of winter in the Antarctic, or getting close to the height of winter. And you're going to see how this evolves or changes over the period of a year as long as it works. Here we go. So I love this video because you can see at the edges, you can see bits coming off and going in, and the gyres and little eddies, and you can see it's getting less and less and growing in other places. So it's a very dynamic system. It's pulsating almost. It's almost like a living organism if you kind of use your imagination. And you can see that there's big patches of open water appearing at the top. And we're getting now, November, we're getting into the height of the Antarctic summer. And we've got a patch left down there and a big patch left in the Weddell Sea up there. But that's all that's left during the summer. We're getting into January, we're getting to the height of summer. And it's almost all gone there, just that big patch left right at the top there in the Weddell Sea. So you've got this dynamic lump of ice that's kind of big in the winter, and it kind of melts to get to nothing in the summer, but there's lots of movement going around on the edges. If you look at the Arctic, it's a similar kind of thing, except that the dates are differently. So in September, we're at the end of summer, and if you look at the similar kind of satellites are brilliant. This is just staggering what you can see this ice sheet, and what's really evocative about this image is just the speed of what is happening. October, you've almost got this continuous sheet over the Arctic Ocean. But again, it's the edges and the patterns and the movement of those edges. You're getting to the height of winter now, and you can see the whole of the Arctic Ocean is just about clear. And you can see little seas here that are also freezing over outside of the main Arctic Ocean, which is there. And then we're going into spring now, into February, and you can see it's beginning to recede a little bit, and you can see it goes back to what it was before. It is important to see that there's places outside of the Arctic that are also freezing over. So that's on the large scale. That's what we're kind of talking about. Now, I was on a ship in 2004 to 2005, and this is how we spent New Year's Day 2005. So we did party, as you would expect, on New Year's Eve, and the next day we had to start work again. So what we did is we put out two buoys, and these buoys were designed that if they are on a solid platform, so if they're on a lump of ice, they would send a signal back to a satellite, which would bounce it back to Helsinki in Finland about every 10 minutes, recording its position, recording the temperature of the air, and recording wind direction or wind speed as well, and some other things. So basically, if it's sending a signal, we know that it's on the lump of ice on which we first put it. Interesting about this, these two buoys are probably between 50 and 100 kilometres apart, so there's a big distance between them. And also it's interesting, any of you who know Shackleton's story and the story of the Endeavour, where the Endeavour went down and then they walked along the ice before they could launch the boats to get to Elephant Island and all the rest of that stuff. Well, the Endeavour went down, round about here. And it's not as if they just had walked and walked all that distance, because we know the ice, because of those tides I talked about at the beginning, the ice is moving in this direction. So the reason Shackleton was so successful, well, he was heroic, and his crew were heroic as well. Of course they were. But the ice was actually moving in this direction, so they weren't walking the whole distance. They were being carried by the ice flows. And that's what the experiment that we wanted to do, is to see whether we could replicate some of that stuff. So again, if you look at these buoys and the date will change across the top. It will change quickly. I'm sorry about that, but you'll get an idea about what happened. So you can see we're already into February, going into March, and you can see they're moving northerly as we would expect. April, getting to May. Then something happens here, quite dramatic. In June, July, this one is hovering around here, but into August, into September. This one has kind of taken off past Elephant Island and is going really quite far north and into November. And we did actually record them a little bit into December, but this little video goes to November. Now, isn't that remarkable? For a period up to this point, they kind of all moved together, or they both moved together. Then this one kind of got taken off down to the left here and then ended up here compared to many thousands of kilometres apart by the end of the year when we stopped, when this video stops. So again, so you've got this movement that you saw in the big videos and that dramatic scale and these big pulsating kind of movements of the whole pack ice zone. And then you can see these various different kinds of movements on a more localized scale over the period of a year. We did another experiment at the same time, which is where we used effectively the ship that we were on, the MOSTYN. It's a German-based research vessel. It's where I've done all my Antarctic work has been on the MOSTYN. It's a brilliant ship. I'll talk about it in a little bit more detail, where we kind of selected an ice flow, and the ice flow was huge. It was several kilometres in diameter, so it's not a titchy bit of ice. It was a massive ice flow. The captain agreed. He cut the engines. He said, throw out an anchor. So we threw out an anchor onto the ice flow, and basically the idea was we were using the whole ship as a massive buoy, rather an expensive buoy, to see where we drifted. And this is the map of the drift. So we cut the engines in November, and the distance between the points is where you travelled in one day. And you can see on this first day we travelled a large distance. Some days we went backwards, and some days we went from side to side. When we went from side to side here, we were caught into a very big spring tide cycle. So we just got caught in a very big tidal cycle where, you know, there was no movement. And so this shows on a much smaller scale the same kind of movements that I've been trying to depict by various means. One thing, if you're trying to do this, if you ever go down to the Antarctic and think I want to do a drift experiment with a ship, the ship, yeah, it was drifting with the underlying currents. But when you put a great big structure like that, it's a very good sail as well. So this movement wasn't just due to the water currents or water, and it was also due to the wind direction, because this was acting as a sail for many of these days when the winds got up. So at various different scales, you get the idea that pack ice is moving and is dynamic. And for anything that's going to live on pack ice, it's got to live with that undercurrent of I wish I hadn't said that. With this kind of underlying dynamic system. So it's not like a lump of earth or a field, which is just static. So any organisms, or a rocky shore, which is pretty static, the organisms that are living there have to live with this dynamism. So, and physics is the key to it all. Now remember, I'm a marine biologist. I enjoy biology. I'm useless at maths, but it's clear to me, and as I've gone on and on and on, it's understanding the underlying physics to a certain degree is absolutely vital. So you have to know about the tides, the currents, the effect of waves, temperature. Obviously, it's got to be cold, but the effect of temperature on the system, the saltiness of the water, as we'll see in a minute, plays a big part in it all, and light for things to grow, of course, but also light because it's a source of heat, it's a source of energy within the system. So although I'm going to talk about biology, it is absolutely important for everything I've spoken about up to now, is that physics is the key to it all. So what's the numbers that are involved? So at its maximum extent, you know, when the biggest blobs were, or the biggest girdle was surrounding the Antarctic continent in July and August, there's about 22 million square kilometres of it. Now, that's a big number, you know that's a big number, but it's pretty meaningless. Its minimum number in summer, when you only have those two blobs left, or that big blob up in the Weddell Sea left, there's about 4 million square kilometres of it. Even now, when I kind of say this, I still don't really have the concept of what that is. So just how much is 20 million square kilometres of sea ice? Just one other factor, most of this ice is about 1 metre thick, about that thick on average. Sometimes it's only that thick, and sometimes it can be over 10. The biggest piece of ice I've ever had caught through is 16 metres thick. Well, 16 metres is a huge lump of ice, but it's not really the same bit of ice. It's just lots of ice rafted on top of each other. But anyway, most of it on average is about 1 metre thick. So that means there's 20,000 cubic kilometres of sea ice at its maximum extent around the Antarctic continent. Pretty meaningless still, I think. So put it another way, there's about 7.6 billion people on the planet at the moment. So that means that every person on the planet, to contain that volume of ice, Your average domestic freezer is about 0.25, about a quarter of a meter cubed. Every person on the planet now would need 12,000 freezers each to contain that volume of ice. Now that's a big number and that's a lot of freezers, and you get the impression. But that means that when this ice is forming, consolidating and then melting, it's such a massive transformation to the poles. So it's happening in the south and it's happening in the north. That is what is driving a lot of ocean circulation. It's driving a lot of the climate patterns. It is such a big thing that is happening on a regular basis to planet Earth that it is controlling a lot of what we see as far as the oceans and the weather is concerned. It is a colossal volume of ice that is moving. Ice is important. I'm not going to talk about these beasts, so I'm getting them over and done with now. But ice is important for birds. And David Attenborough does this much better than I could ever do. You've seen his Frozen Oceans and Blue Planet and all these other things where they show the emperor penguins need the frozen sea ice on which to breed. You've seen the eggs being laid, shuffled into onto the feet of the males who kind of spend the winter huddled together in these freezing conditions on top of ice. And if you didn't have the sea ice, emperor penguins would not be able to breed. So that's important. This is an Adelie penguin. It doesn't breed on ice. It breeds in more northerly climes where there's rocks in the edge of the Antarctic Peninsula and places like that. But it needs sea ice as well. So you can see this kind of a punk version of the Adelie penguin. You can see these feathers that it's releasing. So seabirds, once a year or so, they need to exchange their plumage. They need to change their feathers. When the new feathers come, they're not covered in oil. And it's actually the oils on the feathers that are important for keeping the things buoyant. So if you put a bird with unoiled feathers into the sea, it will just sink. That's what would happen. So while the birds or the Adelie penguins are changing the oils in their plumage or changing their plumage and then getting those well oiled, they need a platform on which to stand, and the sea ice is absolutely vital for that. So some birds use it for breeding, other birds need to change their plumage. Mammals use the ice as well. So in the top you have a charismatic, about 2 tons of a Weddell seal, curious as we went past. Weddell seals give birth to their young on ice. And they actually wean their young on ice as well. They're the mammal with the most southerly distribution. So Weddell seals need the ice on which to give birth and to wean their young. Here's a crab-eater seal, nowhere near as big as the Weddell seal. And the crab-eater seals spend a lot of their time in the pack ice zone. This guy, and I think it was a guy, you can see these 2 wounds down its side. Whenever I give this lecture, sometimes I say it was an orca, a killer whale, and other times I say it was a leopard seal. It's because we don't know what caused these. But it's been attacked by something that wanted to cause harm. And the ice was important for it to get away from the thing that was trying to eat it, but also it stayed here for a good week or so. Actually, it always looked exactly like this. I've often thought it was frozen and dead, but it was alive. It just stayed there for a week or so to actually recover and let the wound start healing before it went back into the water and carried on its merry way. So it's important for getting away from predators as well as for the Weddell seals. And there's a lot of it. So you see each one of those black blobs in the background. Each one of those, this is a picture taken at noon at lunchtime. Each one of those black blobs is 2 tons of Weddell seal. They used to feed during the night, and in the mornings they used to all pop up at lunchtime, have a snooze for a few hours before going back and feeding for the rest of the evening. That's a lot of animal when you count all those black blobs up. This is the edge of the Adelie penguin colony. This is really the very edge. There were thousands of them behind the picture. So there's an awful lot of these organisms within it's one of the beautiful things about working in that part of the environment is that you do get to see this kind of thing. Well, you can only have a lot of this kind of stuff if there's a lot to eat. So there's got to be something that they're eating to be able to create that amount of biomass. And you will hear it, and you probably, many of you have heard it before, but there is an organism down there, this thing, the krill, shrimp-like organism. I don't know, an adult krill is about that kind of long. you know, 4, 5 inches long when it's adult. And the krill are there in humongous numbers in the Southern Ocean. I've never seen it, but apparently when you really get a krill swarm in the surface of the ocean, when a ship goes through a krill swarm, the bow wave is blood red. It must be spectacular to see. I've seen krill under the water and underneath ice, but I've never seen them where the ship is causing this blood red bow wave. And all of these organisms, it's called the linchpin or the central point of the Southern Ocean ecosystem because, you know, the birds are eating it, the penguins are eating it, seals are eating it, squid are eating it, whales migrate in the summer to eat krill as well, and so does some fish as well. So there's a lot of things. So if you've got all of this biomass of penguins and squid and so on, you've got to have a lot of krill to support it. You know, and that's where people, this is now you're going to see what kind of biologist I am, because you've got to delve back further. You can only have these humongous amounts of krill if you have a lot of stuff in the ocean that the krill are eating as well. So you can't have tons of krill if you don't have 10 tons of stuff for it to eat. And that's the algae, the bacteria and protozoans. And those are the things that, unfortunately for you, that's the things that are kind of fascinating me for most of my scientific career, is the food stuff that supports all the rest. And that's what we're going to talk a little about in a minute. So lots of big things there because there's lots of krill. There's lots of krill because there's lots of small things. Okay, so sea ice research. We've had about 150 years of research. On the left, this is a picture, a really famous botanist, scientist, explorer, Joseph Hooker, went down in about 1842. And what he did is he took a lump of ice from an ice floe, he melted it, looked down his microscope, and this is what he drew. He drew some round things, some pencil-like things, and some of these pencil-like things were growing in chains as well. And it's probably one of the first. There was a bit of a war going on between a guy in Germany called Ehrenberg and Hooker as to who was, you know, I think actually Ehrenberg probably made the first drawings, but we'll put the UK scientist up here. But it was around in the 1840s the first pictures were being drawn. I've got a colleague in 1990, Annette Bartsch, who did exactly the same thing, got a lump of ice, melted it, looked down the microscope, but you know, things have moved on a little bit from Hooker's day. She could actually take a photograph, and she saw exactly the same thing. She saw some round things, some needle-like things, and some things growing in chains as well. And I just think the symmetry of 150 years between these two scientists on a research ship doing exactly the same thing with just slightly different tools, looking at the same picture, I just think is an amazing statement in a way. And to be quite honest, it's more of an amazing statement about just how good these guys were with their rudimentary techniques that they had. And since the 80s, there has been a revolution in the way that the sea ice research has been able to take off. So Hooker went in wooden ships, and they could only go a certain way into the ice, and because they could. So we go on ships like this. There are very few real icebreakers in the world. So you've all heard about Boaty McBoatface, or the Sir David Attenborough, as we should really call it, which was launched in Camel Lead, went into down the slipway a few months ago now, and we'll go to sea trials in the next 12 months. So that's great. But that's how can you have a ship? You normally refer to a ship as a she. How can you have the Sir David Attenborough? It just doesn't ring true anymore. But anyway, so every time I say she, I kind of think, am I allowed to say that about the Sir David Attenborough? Anyway, it can break ice, but it can't go deep into the pack ice. So the Australians have a proper icebreaker that can really go deep into pack ice. The Germans, the Canadians, as you would expect, the Americans have a few, and the Finns and the Swedes. But there's very few icebreakers. This ship has been going quite a long time, the Polarstern, Polar Star in English. She's designed that if she does get stuck, she can survive a whole year down there. It's quite remarkable if you listen to the captain. They've got it so they know that if things start getting really ropey and you're running out of fuel and food and stuff, There's special rooms in the ship where everybody will eventually congregate. They know how much wooden furniture is on the ship so that it can be burnt should more energy be needed. So there's a very good strategy that they've never had to use should the ship have to be there for longer periods of time. Most of my trips on the ship are 3 to 4, mostly 3 months, sometimes 4 months as well. It's designed to get completely covered in ice. They're beautifully designed ships, and they're designed to get covered in ice, thousands and thousands of tons of ice covering the ship when this picture was taken. There's a couple of helicopters on board, which mean that you can have remote stations away from the ship. Most of the time, you get on and off, they just put a gangway onto the ice and you can get on and off the ship as well. And having access to these kind of facilities is what has revolutionized the sea ice research that I'm talking about today. But it's not, this is the Bangor contribution. Now you laugh, and everybody always laughs. But you see, all of that German engineering and that mighty power of the Polarstern, that got us to where we wanted to be. But it couldn't get us in between these ice flows, and it couldn't get us to where we really wanted to be. So Bangor came along with a partially inflated, and that was great. It's partially inflated because the ice is really hard. And so if we had bounced up against an ice flow with a hard, fully inflated rubber boat, it would have just been ripped to shreds. So, it was only partially inflated. But so there's a part of it you need the might and the power, but you also need a little bit of ingenuity and some creativity. I don't know, hope none of you are health and safety executives or people at work, because it's very clear that we're not wearing our life vests in that picture. Anyway, so what is ice? So this is a colleague of mine working on top of the ice, and it's covered in snow, and it looks frozen and cold, and it looks hostile. Right. So this is where you're going to have to use a little bit of imagination. So if you freeze ice cubes in tap water in your freezer at home at minus 18 degrees, or depth of winter, the lakes up on the mountains, they freeze over a little bit, or your pond in your garden or your bird bath freezes over. You take that ice and you throw it on the floor, it will shatter into shards really hard. And there'll probably be a twinkling noise as well, or tinkling noise as well. If you do the same thing with a lump of frozen seawater at the same kind of temperature, you'll get more of it will shatter, but it actually will break apart. It'll be more like a pudding. It will go brr. It will you won't get these hard shards. Now the reason for this is because only pure water can form an ice crystal. And you know that seawater contains a lot of salt. There's normally 35 grams per every litre of seawater, and it contains a lot of dissolved substances as well, gases, lots of minerals in there as well. So as the ice crystal is growing, all of these other dissolved substances are pushed away from the growing edges of the ice crystal. And they're pushed away, and they collect in a series of channels and pores in between the ice crystals. Now the ice continues to grow and consolidate, and so therefore the concentrations of all of these substances increase as there more and more ice forms. So this is where you've got to use your imagination. If you think about a Swiss cheese or a sponge, and the hard part of that cheese on the hard part of the sponge is ice, pure water, and then in between that, in the channels and pores permeating through the hard bits, is this very concentrated brine solution. So what you have here is that basically these channels and pores, the ice has been melted away from them, and you're kind of left with this impression of what is really a liquid labyrinth. Now you can see it in the next picture here. So this is a slice of ice, and you can see this channel coming down, and you can see this kind of ends in this convoluted pocket at the end, which isn't connected to anything else. And this is one of those channels. And you can see these brown blobs that are inside of them. Now, these brown blobs are algae, and we're going to come back to them in a minute and why those are important. So ice crystals here, a channel, a pore filled with really salty brine solution. Very much more salty than the stuff than seawater. In fact, the amount of salt, so at about minus 15 degrees centigrade, so that's really quite low. There's a lot of ice, there's very small channels, and the concentration of the the saltiness of the water, the salinity of the water, is about 2 or 3 times that of normal seawater. So it really is very salty. So if things are growing in there, they must be able to withstand growing across a whole range of temperatures and also saltiness in the water as well. And we'll come into that as why that could be important a little bit later. These brown blobs, so this is, if you remember, is the picture that colleague Annetta Bartsch took in the early 1990s, are diatoms. Diatoms are a small kind of algae. You get diatoms just about everywhere. So diatoms grow in rivers, on stones, they grow in all seawaters around here. They grow in the tropical waters. They're a ubiquitous type of algae, but they photosynthesize, so that means they trap light energy and they convert that light energy into new biomass. And they have chlorophyll and other pigments, so just have chlorophyll just like grass and trees have chlorophyll. So they've got green stuff in them that traps that. But they've got other pigments, and these other pigments are what make them look this golden brown. So these other it's not just chlorophyll, these other pigments make it look these wonderful golden brown colors as well. So diatoms are the key player. Diatoms, what is remarkable about a diatom and why I enjoy them so much is it looks as though they've got clear shells around their cell contents. Now these shells, in inverted commas, they're called frustules, but let's call them shells for now. They're made of effectively glass. So they're basically glass shells. Now you think glass, fragile, no, that's not going to work, ice and all these things. But those glass shells are incredibly tough. They're really, really tough. And well, if I ever get invited to give the other lecture, I can talk about glass shells then. But so they're tough. And so there's so many of these diatoms that quite often when you pass through, when the ship's passing by, an ice floe like this, and the ice floe is rocking in the wake of the ship, you get a view of the underside of the ice floe, and there's so much biology there. There's so many diatoms there that actually it's this golden coffee color ice. And then quite often you hear people talking about, oh, there's a load of brown ice outside, and the biologists are kind of interested. So it's not this frozen white desert that you kind of imagine the pack ice to be, but actually just under the water surface, there's a lot of life going on. The early sealers and the whalers that went to the Antarctic to get penguins, whales and seals, they were the first ones to really make this link, because they made this link, hang on a minute, wherever they found a lot of brown ice, they normally found accumulations of the things that they were looking for. And so they actually used to log in their logs, in their ship's logs, areas where there was a lot of brown ice. And that would be, when they went back the following year, they would know that they would likely to find lots of seals and whales. So they kind of made the link between the ecology in the ice and those other trophic layers that are so charismatic. Now this seems a little bit up. There's a moon of Jupiter called Europa. On the moon of Jupiter, called Europa, there's a sea. Now on Earth, planet Earth, the sea is made, the salts is mainly sodium chloride. On the moon of Jupiter, the salts in the sea is magnesium sulfate. It doesn't really matter, it's a very salty ocean. And there's tides, and the oceans are moving it. And wonderfully, it's covered in a load of ice. And when you look through a microscope at it, or use a microscope, you can see these big brown striations of colour going through the ice. And there's Sir Fred Hoyle in the 1980s, and Fred Hoyle was the astronomer royal. He did an amazing job of bringing science to non-specialist audiences and bringing astronomy, him and Patrick Moore, I guess. And he said, and it's a brilliant paper, he said, well, we know there's brown ice on the oceans down on planet Earth, and we know there's brown ice up on the moon of Jupiter. So it's pretty clear. That's a load of diatoms up on Jupiter, on the moon of Jupiter, just like they are down in the Antarctic. I don't know. What I would say, it has spurred a lot of research interest. People pay researchers, certainly in the States, a lot of money in the field of astrobiology, so studying how organisms survive hostile conditions on Earth as a proxy for what may happen up on Europa. I don't know. I don't believe there are diatoms on Europa, but who knows? And one thing I'm certain is there's not going to be penguins up there. I mean, I just don't believe it, but I guess you never know. Okay, it's not just algae. I mean, algae are a passion of mine, and I think they're great, but they're not just there. So here's an alga. Here's an alga-like thing. And these little dots here are all bacteria as well. So you can see that, again, this is just some melted seawater and sees what's there. So there's an awful lot of bacteria within the system as well. And we know recently there's lots of viruses in ice as well. So there's lots of things eating these algae and this bacteria. So there's things like these amphipods, these shrimp-like, you see them under the seaweeds on the shore here. So amphipod-like creatures. This is a ciliate, so this is it's covered in cilia, and ciliates are great because they can change their body shape to twist and turn into this labyrinth of these channels and pores, seeking the food, which is the algae and the bacteria that they want. So they can change their shape dramatically, and there's lots of other organisms that can. This big critter on the top there, it's pretty restricted to the bottom of the ice. Why I put lumps of poo up here is kind of an interesting thing. So all of these things produce poo at the end of the day. And we say, well, why on earth is that interesting, David? Well, it is in a sense because balls of poo like this transfer down the water column, sink really very much faster than if all of these cells were on their own as individuals. Well, why is that important? Well, that's important because there's a whole load of organisms living on the bottom of the sea that are reliant on stuff raining down from the top on which they feed. They filter all of this material coming out of the seawater. So if it's very much faster, it gets down to the bottom very much fresher and much better nutritional value as well. And you would have seen on many BBC programs these very rich underworld views of the bottom of the Antarctic Sea as well. And one of the reasons that it's so rich and these organisms are so large is because they grow very slowly and don't often get disturbed. But also, there is this rich rain of food coming down from above. And so even the poo that these things are producing is important. So there's a whole network of organisms that are in the ice and grazing on the underside of the ice. And they're not all micros. Some of them, like the krill, as you see, can only, they're so big. So basically, these channels, it's a bit like the spy espionage films where the hero has been thrown into the car crusher, and the sides are kind of coming down onto the hero that's in this car crusher. And that's what it's like from an organism in the sea ice. It's basically, as the ice gets colder and more ice grows, those channels get smaller and smaller and smaller till you get to about -20, when actually there's only enough space in these channels for a bacteria or a virus to live. So a lot of these larger organisms are just restricted from these channels because they're just too large, especially things like the krill and these small fish. It's not a very good picture, but at the top you can see you can see the black blobs. Well, they're polar cod, so they're Arctic fish that are growing up, hiding between the underside of ice floes that are rafted on top of each other. And there's a whole realm of, well, not particularly attractive looking organisms that are living in the ice, but they're feeding on this rich diatom diet that is in there. Some of them are just curious, and I just love them. And one of the reasons I study marine biology is actually I just love looking at the myriad of forms that evolution has thrown up. And this is a bit of a Starship Enterprise picture, isn't it? Some are just really curious mini spaceships, and you just think, well, why wouldn't you want to study these things when they look like that? And that's great. Okay, so the other thing I haven't spoken a lot about is low and high light. So it's light, but it's pretty intuitive. If you put a slab of ice covered with some snow on top of the sea, it's quite clearly that the light it's difficult for much light to get through that. It's a very effective preventer or barrier to light. So, but also if an ice floe breaks apart, all of a sudden there can be a high light environment. So the organisms that are growing there see a variety of low and high lights. for most of the winter, it's really very low light. But in the spring and the summer, the Southern Ocean is a very high light environment. So they have to be able to cope with high and low salinities. I talked about how the salinities in the brine channels are really very high, 2-3 times seawater concentrations. When the ice melts at the end of the season, there's a lot of fresh water released as well. Low temperatures goes without saying. You know, ice is cold. Seawater freezes at -2 degrees. Because of the salt that's within it, it doesn't freeze at 0 degrees like fresh water does. It's at -2 degrees. But temperatures in ice, you know, that we've measured down to -20 routinely. So anything that's surviving in the ice has to cope with a very big range of temperatures. And the restricted exchange just means is there's not much, you know, it's stuck in a channel in port. Most of these organisms come from the open ocean where, you know, water exchange and exchange of nutrients and gases is unlimited because they're just surrounded by water. But all of a sudden they find themselves in this environment by which, you know, gases and waste products and things aren't easy to exchange like before. Now, so here's some real hardcore chemistry, I'm afraid. So the high salinity, high saltiness of these brine channels, the low temperatures enhance this stuff called DMSP. Now, DMSP is dimethylsulfoniopropionate. Now, I'd just be curious to know how many of you have remembered dimethylsulfoniopropionate by tomorrow. It's DMSP is great. So you think, oh, and it's basically the algal cells in the ice. They use it as an antifreeze. So they build DMSP up in their cells, and it's a really good antifreeze. It stops ice crystals nucleating. It stops them actually growing inside the cells. They also use it to change their osmoregulation. So they change it as the salinity changes and the concentrations of substances outside of the cells changes. They have to change the concentrations of substances within the cells to keep the balance between the outside and the inside. And DMSP is a really good thing for changing that balance as well. And it has some other properties as well. But mainly it's this combination of it helps them withstand salt change, and it helps them withstand temperature change as well. So high salinity, or basically conditions you get in winter in ice, means that there's a lot of DMSP. Stick with me, it's really exciting. What would you prefer, pictures of penguins or DMSP? Anyway, don't answer that. Ice algae are linked to the historical record of sea ice, and this is where it gets really exciting. So this is the kind of chemistry I like. DMSP is broken down, when it's degraded, into a gas called DMS, dimethyl sulfide. So you've got ice, creates a lot of DMSP inside the organisms that release that stuff, and it's broken down to DMS. DMS, when it's released into the atmosphere, so it leaves the water and it's released into the atmosphere, that's oxidized into this thing called MSA. So DMSP, DMS, MSA. Again, stick with me. So this is the chemistry that's going on. Lots of sea ice means lots of ice algae, which means lots of DMSP, which means lots of DMS, which means lots of MSA. That's the kind of the theory. Now, why MSA is important is that actually is oxidized in the atmosphere to form clouds. So if you have, I just love it, you've got this thing where you get a lot of sea ice producing a lot of sea ice algae that effectively means that there's a lot of cloud production going on once all of this gas gets up into the atmosphere. So that's interesting. So that's this link between algae and the atmosphere, but it gets even more exciting than that, because you can take an ice core on the continent, and you've all heard the pictures about how we got over millions of years the ice record of the CO2 and the temperature record in the ice cores, and these are because they kind of like this, 3 to 4 kilometers of ice that they chop up into very fine, and each fine section is equivalent to a year. And you can do this in many parts of the Antarctic, but this is stuff that was done by the Australians the Australians who are working at a place called Lordorm, and these colleagues, they just drilled a core through the continental ice and then shaved it up. And what they found is that the MSA that had been released into the atmosphere is pretty well preserved along with the CO2 and all the other gases that are interested in these big, deep historical ice cores. So if you measure the MSA concentration at different levels through the ice, remember I said it was just frozen snow at the beginning, you potentially have a record of MSA for hundreds or tens or hundreds of thousands of years, just like we have the temperature record from the carbon dioxide concentrations as well. And now that really is exciting. Sea ice algae producing something to protect themselves from freezing and saltiness actually are giving us a record of what the previous sea ice record was. So, you saw those videos I took, we're nearly there, don't worry, we're nearly finished. You saw those records that I showed you of the satellite images of the sea. So you can actually get a pretty good minute by minute impression of where the sea ice is using satellite information. There's websites out there that are just brilliant. They show you these in clear color. So we've got basically, you can make a measure of the sea ice extent in whatever you want. And here's the data where they measured the sea ice extent in blue, and then they took the slices of the ice from the continent and actually measured this MSA concentration inside these ice cores. And lo and behold, they got this really good match between the sea ice extent from the satellites and the MSA concentration in the ice. Brilliant. And they could put a line through it, and it looks as though between 1978 and 2005, I think we were probably up here, there was a slight increase in both of the records in sea ice extent and MSA. So they went backwards, as you would expect them to do, and they went back into the 1940s, and again, they got the MSA concentration. The only problem is they don't have, the satellites only started taking the pictures in the 1970s, so that's where our satellite. So actually, if you look at it historically, what's interesting, you can see these big dips and troughs and peaks in the MSA record, which would indicate that there's a lot of change going on in the pack ice here. And actually, instead of there being a slight increase, when you do the stats, there's actually, between the 1940s and the 2000, there's actually a decrease in the sea ice rather than the increase that was indicated by just having the first figure that I showed you. And of course, they've gone back further and further. 1814, actually, there are some. This was Curran's paper that was in 2003. They've gone back even further in later papers, but you can see that over time, from 1840 to 1940, everything was kind of basically stable. There was a lot of wiggling around this black line, but it was effectively stable. But you can see this dramatic decrease since the 1950s towards the end of this thing. So this was recording. So I think it's a brilliant. I just love this concept as a biologist that actually, and of course, who knows? And this is the work they're doing at the moment is going back as far as they possibly can. And of course, they want to go back to the hundreds of thousands of years if they possibly can. Oh well. You can ask questions if you're interested. I can tell you why there's a little bit of doubts. But what is really fascinating is that it's actually these little critters within the ice that are potentially ultimately going to give us this amazing record of what previous ice history was on the globe. And I just think, as a biologist, it gives you a big buzz when you kind of realize the stuff. I've been studying temperature and salinity tolerance or saltiness tolerance in these things, thinking, well, it's curious and it's scientifically interesting, but actually, as a result of that, we may actually find out what's going on over millions or thousands of years at least. Okay, and that's where I want to end. So that's a roundabout trip of the biology in the ice that I've been doing in the pack ice, and of course I'm open to any questions should you have them.